Imagine accelerating forever, engines roaring, stars blurring into lines as you hurtle toward the edge of the galaxy. But no matter how much fuel you burn, something invisible slams on the brakes. You creep closer to that ultimate barrier, the speed of light, yet never quite touch it. Why does the universe enforce this unbreakable rule that dashes our dreams of zipping between stars? Today we uncover why nothing can go faster than light, a cosmic law etched into reality itself. This fundamental limit isn't some random cap, it's the heartbeat of spacetime, governing everything from subatomic dances to galactic collisions. Albert Einstein unlocked it over a century ago with special relativity, but modern labs and telescopes confirm it daily. Everyday intuition fails us here. You push a car pedal, it speeds up endlessly, but near light speed, reality rebels. Objects gain relativistic mass, not their rest mass, but the inertia resisting acceleration swells dramatically as velocity climbs. At half light speed, an object's effective mass roughly doubles. Hit 90%, it's over 2.5 times heavier. 99%? More than 7 times. 99.99%? Over 70 times. The fuel needed explodes exponentially just for tiny speed bumps. Infinite energy would be required to reach exactly light speed for anything with mass. Picture squeezing all stars' output into one proton, still not enough. Photons zip at light speed because they're massless, gluons too. Anything with even a whisper of mass hits this wall. Experiments scream confirmation. The Large Hadron Collider smashes protons to 99.9999% light speed. They behave exactly as predicted, heavier, time-stretched, paths curving precisely. No violations, ever. Time dilation adds the twist. Fast movers age slower relative to stationary observers. Muons from cosmic rays, normally decaying in microseconds, live longer at near-light speeds, raining deeper into Earth's atmosphere before vanishing. Proved in labs since the 1940s. GPS satellites orbit at 12,500 kilometers per hour. Without relativity corrections, both velocities slowing their clocks and weaker gravity speeding them, your phone's location would drift 11 kilometers daily. Real-world proof in your pocket. Hey, if this unraveling of cosmic rules has you hooked already, smash subscribe and thumbs up now. Your support keeps these universe explorations coming strong. Space-time itself enforces the rule. Space and time fuse into a four-dimensional fabric where light speed is the conversion factor. Events connect via light cones, future possibilities bounded by light's reach. Faster than light? It scrambles cause before effect. Causality crumbles without it. Send a signal backward in time via superluminal tricks, and paradoxes erupt. Kill your grandfather before you're born. The universe abhors such nonsense, preserving logical flow. Quantum mechanics tests the boundary too. Entangled particles correlate instantly across distances. Einstein's spooky action. But no info transfers faster than light. Bell tests since the 1980s, loophole-free since 2015, uphold this. Correlation without communication. Gravitational waves from black hole mergers detected by LIGO in 2015 ripple spacetime at precisely light speed. Binary neutron stars in 2017. Light and waves arrived together, billions of light-years traveled in sync. No shortcuts. The cosmic microwave background relic glow from 380,000 years post-Big Bang shows uniform speed limits across 13.8 billion light-years. Early universe obeyed the same law as today's particle smashers. Even universe expansion dances around it. Distant galaxies recede faster than light via stretching space, not motion, through it. Hubble's law, refined by James Webb's 2022 deep fields, confirms space expands freely, contents don't cheat locally. This invariance anchors the universe's story. Quantum fluctuations seeded galaxies under the same rules photons now obey. From Planck epoch's fiery birth to now's vast web, light speed threads causality unbroken. Competing ideas? Tachyons, hypothetical faster-than-light particles, predicted backward time cones, decades of hunts at CERN, Fermilab, zilch. Variable speed theories tweak fine structure constant over cosmic time. Controversial quasar data hints, but supernova surveys favor constancy. We're stardust questioning the forge that birthed us, iron in your blood, carbon in cells, supernova ejector, flung sublight speeds, faster, chaos, elements arriving pre-announcement, this limit sculpted stable atoms' life, you pondering it. The speed of light travels at precisely 186,282 kilometers per second in vacuum. That's 670 million kilometers per hour, or about 7 times around Earth's equator in one heartbeat. Yet this blazing pace becomes a crawl against cosmic distances. Light from the Sun takes 8 minutes, 19 seconds to warm your face. From Neptune? 4 hours. From Proxima Centauri, our nearest stellar neighbor, 4.24 years. This finite speed transforms telescopes into time machines. When you glimpse Andromeda Galaxy with naked eyes, you're seeing it as it existed 2.5 million years ago, when early humans first walked upright. The Hubble Space Telescope peers 13 billion years backward, capturing infant galaxies forming when the universe was just 5% its current age. We never see the universe as it is, only as it was. Think about that deeply. Every star you see tonight might already be dead, its final light still racing toward us through the void. Betelgeuse, Orion's red supergiant shoulder, sits 650 light-years away. If it exploded yesterday, we won't witness the spectacular supernova until the year 2674. The cosmos is a museum of light, preserving history in photons. Modern physics reveals even stranger truths. Mass and energy intertwine through Einstein's famous equation, E equals mc squared. As you accelerate, kinetic energy transforms into mass energy, making further acceleration harder. It's not that engines fail, reality itself resists. The universe conspires to protect its speed limit through the very fabric of existence. Particle accelerators demonstrate this daily. SLAC's linear accelerator pushes electrons to 99.999995% light speed across 2 kilometers. Those electrons become 4,000 times heavier than at rest. Scientists must account for this mass increase precisely, or particles miss targets entirely. Theory matches experiment to 12 decimal places, nature's most accurate agreement. But why this specific speed? Why 186,282 kilometers per second, not faster or slower? The answer lies deeper than measurement. Light speed emerges from space's electric permittivity and magnetic permeability, fundamental properties determining how fields propagate. Change these constants, atoms collapse, stars can't shine, chemistry fails. Our universe's speed limit enables its very existence. Consider neutrinos, ghost particles barely interacting with matter. Trillions pass through you each second from the Sun. They have tiny mass, racing at 99.99% light speed or higher. The Opera experiment in 2011 briefly thought they exceeded light speed between CERN and Italy. Headlines exploded, but a loose cable caused timing errors. When fixed, neutrinos obeyed perfectly. Even nature's most elusive particles respect the limit. Space missions feel this tyranny acutely. Voyager 1, humanity's farthest artifact, launched in 1977, now cruises over 15 billion kilometers away at 38,000 kilometers per hour. Impressive? That's just 0.0056% light speed. Reaching Proxima Centauri would take 73,000 years. Our fastest probe, Parker Solar Probe, touched 430,000 kilometers per hour near the Sun, still only 0.064% light speed. Radio signals obey too. Commands to Mars rovers face 4 to 24-minute delays depending on planetary positions. Operators can't steer in real time. Rovers must navigate autonomously. New Horizons' Pluto flyby in 2015 involved 5-hour signal delays. By arrival time, any course correction would be ancient history. Light speed doesn't just limit travel, it isolates us temporally. The cosmos uses this isolation creatively. Every point in spacetime has its own light cone, regions of past that could influence it and future it could affect. Events outside your light cone literally cannot touch you, nor you them. You're causally disconnected from most of the universe at any moment. This isn't loneliness, it's fundamental structure preventing paradoxes from tearing reality apart. Black holes epitomize light's limit. Their event horizons mark where escape velocity equals light speed. Inside, space flows inward faster than light can swim upstream. Not even information escapes. Stephen Hawking showed quantum effects slowly evaporate them via radiation at the horizon, but this too respects light speed. Black holes are cosmic sensors, hiding singularities where physics breaks down behind veils that light cannot pierce. Gravitational lensing showcases another facet. Massive objects bend space-time, curving light paths around them. Galaxy clusters act as natural telescopes, magnifying distant objects via gravitational focusing. The light takes longer curved routes, arriving delayed. Some quasars appear quadrupled, each image showing different moments, as light traveled various paths. We see cosmic instant replays courtesy of light speed's finite nature. Dark energy accelerates cosmic expansion, discovered through supernovae observations in 1998. Eventually, galaxies beyond our local group will recede faster than light via expanding space between us. Their light will redshift to invisibility, leaving our descendants in an island universe. The observable cosmos shrinks even as total space grows. Light speed can't keep pace with accelerating expansion. Quantum entanglement seems to violate the limit but doesn't. When particles entangle, measuring one instantly affects the other regardless of separation. But no usable information transmits faster than light. You can't encode messages through entanglement alone. Classical channels limited by light speed must accompany any quantum communication. Nature permits instant correlation but forbids instant conversation. The Alcubierre drive offers a theoretical loophole. Proposed in 1994, it warps space to move faster than light without locally exceeding the limit, contract space ahead, expand behind, surf a space-time wave. But it needs exotic matter with negative energy density, never observed and possibly impossible. Even if feasible, creating the warp bubble requires superluminal coordination. A catch? 22. Wormholes provide another speculative shortcut. These space-time tunnels could connect distant regions, allowing apparent faster-than-light travel by shortening the distance. But traversable wormholes need exotic matter too, and would likely collapse instantly without it. Plus, they might enable time travel paradoxes. Most physicists doubt nature permits such causality violations. The hunt for loopholes continues because human curiosity refuses boundaries. Scientists at NASA's EagleWorks laboratory investigated exotic propulsion concepts, including testing electromagnetic drives that seem to produce thrust without propellant. Initial results sparked excitement, but refined experiments revealed measurement errors. No reactionless drive has survived scrutiny. Conservation laws hold firm, yet nature surprises us constantly. Quantum tunneling allows particles to penetrate barriers they shouldn't classically cross, appearing instantly on the other side. Does information travel faster than light during tunneling? Experiments say no. The wave function's leading edge still respects light speed. Even quantum mechanics' weirdest tricks obey the cosmic speed limit when information transfer is measured carefully. Cosmological inflation poses fascinating questions. During the universe's first 10 to the negative 32 seconds, space expanded by factors of 10 to the 26 or more. Regions separated faster than light could connect them. This explains why the cosmic microwave background looks nearly identical in opposite directions. Those regions were once neighbors before inflation flung them apart. Space itself has no speed limit, only things moving through space do. The holographic principle suggests reality might be even stranger. Black hole thermodynamics implies information isn't stored in volumes but on surfaces. Some theorists propose our three-dimensional universe is a projection from information encoded on a distant two-dimensional boundary. If true, the speed limit might reflect processing constraints of this cosmic hologram. We could be living in the universe's ultimate simulation, with light speed as its refresh rate. String theory, attempting to unify quantum mechanics and general relativity, predicts extra dimensions beyond our familiar four. These could be microscopic, curled up smaller than atoms, or vast, with our universe a membrane floating in higher dimensional space. Some models suggest gravity leaks into extra dimensions, explaining its weakness. Could shortcuts through these dimensions bypass light speed? The math allows it, but experimental evidence remains elusive. The many-worlds interpretation of quantum mechanics proposes parallel universes branching at every quantum event. In this view, faster-than-light travel might be impossible within any single branch, but irrelevant if all possibilities occur somewhere. Your parallel selves explore every permitted path through space-time. This doesn't help us travel faster, but it reframes what travel means in an infinitely branching multiverse. Let's ground ourselves with concrete experiments. Atomic clocks flown on airplanes confirm time dilation precisely. The Haffel-Keating experiment in 1971 flew cesium clocks around Earth, comparing them to reference clocks. Eastward flights lost 59 nanoseconds, westward gained 273 nanoseconds, exactly matching relativity's predictions. Your flight to another continent literally ages you microseconds less than staying home. Cosmic ray muons provide natural experiments. Created when cosmic rays strike atmosphere molecules, muons live only 2.2 microseconds at rest. They shouldn't reach Earth's surface from where they form, 10 to 15 kilometers up, but time dilation at 99.8% light speed extends their lifetime enough to shower down on us. Mountaintop experiments since the 1960s confirm this perfectly. Particle physics depends entirely on light speed's constancy. Every calculation in quantum field theory assumes Lorentz invariance, that physics looks identical to all observers regardless of motion. This symmetry directly implies nothing exceeds light speed. The Standard Model's spectacular success, predicting particle properties to incredible precision, validates this foundation billions of times daily in accelerators worldwide. The cosmic speed limit shapes astronomy profoundly. Type Ia supernovae, used as standard candles to measure cosmic distances, shine predictably because white dwarfs explode at a specific mass limit. Light from these explosions carries information about expansion history. Dark energy's discovery relied on comparing nearby and distant supernovae, their light separated by billions of years travel time. Without light speed's constancy, Such measurements would be meaningless. Pulsars, rapidly spinning neutron stars, beam radio waves like cosmic lighthouses. Millisecond pulsars rival atomic clocks in precision. Binary pulsars orbit companions, allowing tests of general relativity in extreme gravity. The Hulse-Taylor binary, discovered in 1974, loses orbital energy exactly as predicted by gravitational wave emission at light speed. 30 years of observations match Einstein's theory to 0.2% accuracy. Fast radio bursts discovered in 2007 flash millisecond radio pulses from billions of light-years away. Their dispersion through intergalactic plasma reveals matter density along sightlines. Some repeat, others don't. Their origins remained mysterious until recently. Magnetars, ultramagnetic neutron stars, likely cause many. These cosmic flashes probe the universe's structure, but only because radio waves travel at light's constant speed through varying media. The James Webb Space Telescope pushes observations to new extremes. Its infrared vision penetrates dust clouds and detects redshifted light from the universe's first galaxies. In 2022, it spotted galaxies existing just 300 million years after the Big Bang. Their light traveled 13.5 billion years to reach us. We see baby galaxies that might have already collided, merged, or died billions of years ago. LIGO and Virgo. Gravitational wave detectors measure space-time ripples from colliding black holes and neutron stars. These waves travel at light speed, confirmed when gravitational and electromagnetic signals from merging neutron stars arrived simultaneously after journeying 130 million light-years. This observation, designated GW1787, killed modified gravity theories proposing different speeds for gravity and light. Breakthrough Starshot, announced in 2016, aims to send tiny probes to Proxima Centauri using powerful lasers. Light sails would accelerate gram-scale spacecraft to 20% light speed, reaching our nearest star in 20 years. Even this ambitious project respects the limit, using light itself for propulsion. The engineering challenges are immense, but physics permits it. Cultural implications run deep. Science fiction must grapple with light speed or ignore realistic space travel. Star Trek's warp drive, Star Wars hyperspace, Dune's spice-powered navigation all imagine workarounds. These stories reflect human yearning to transcend limits. Yet the most compelling space narratives often embrace the limit, exploring its consequences for isolated colonies and time-dilated travelers. Philosophy wrestles with implications too. If nothing travels faster than light, free will faces scrutiny. Your future light cone contains all possible events you could influence. It's predetermined in shape, if not detail. Does this geometric constraint on possibility challenge human agency? Some argue the universe is block-like, with past, present, and future equally real. We just experience one slice at a time. Others maintain quantum uncertainty preserves genuine choice within light's boundaries. The anthropic principle emerges naturally. If light speed varied significantly, atoms couldn't form, stars wouldn't shine, chemistry would fail. We observe this specific speed because alternative values prevent observers entirely. This isn't mystical, it's selection bias. Universes hostile to complexity contain no one to measure their constants. Our existence requires light speed's precise value. Communication with extraterrestrial intelligence faces light speed's tyranny. Radio signals from Earth have reached only stars within 120 light-years since Marconi's first transmissions. That's infinitesimal compared to our galaxy's 100,000 light-year diameter. If civilizations typically last mere thousands of years, the window for dialogue shrinks dramatically. We might be surrounded by intelligence but isolated by time and distance. SETI searching for extraterrestrial signals since 1960, confronts this reality. Even detecting a signal doesn't enable conversation. A message from 1,000 light-years away describes a civilization from Earth's Middle Ages. Our response wouldn't arrive until the year 4024. By then, both civilizations might be extinct or transformed beyond recognition. Light speed makes the universe a lonely place. Yet isolation might protect us. The dark forest hypothesis suggests civilizations hide because revealing location invites destruction. If hostile forces exist, light speed limits their reach. Earth broadcast its presence just over a century ago. Any response, friendly or hostile, from beyond that expanding sphere remains physically impossible. The cosmic speed limit grants us time to mature before facing whatever lurks among the stars. Closer to home, light speed affects daily technology. Computer chips face fundamental limits as transistors shrink. Signals between components can't exceed light speed, creating bottlenecks. Modern processors use multiple cores partly because single cores hit speed walls. Quantum computers might calculate faster, but still can't transmit results faster than light. Information technology bumps against Einstein's ceiling. The internet experiences light speed lag constantly. Undersea cables carry data between continents at about 2/3 light speed through fiber optics. New York to London takes minimum 28 milliseconds. High-frequency traders locate servers near exchanges because every millisecond matters. Satellite internet adds delays as signals travel to geostationary orbit and back. Zoom calls to the space station show noticeable lags. Light speed isn't just cosmic, it shapes global communication. Medical imaging relies on light speed's constancy. MRI machines detect radio waves from hydrogen atoms in your body. PET scans track gamma rays from radioactive tracers. Ultrasound uses sound waves, ultimately limited by electromagnetic forces between atoms. Every medical scan depends on signals propagating at predictable speeds. Without light speed's reliability, modern medicine couldn't peer inside living bodies. Materials science pushes boundaries within limits. Metamaterials with negative refractive indices bend light backward, cloaking objects or focusing beyond diffraction limits. Photonic crystals slow light to walking speed or stop it entirely, storing information in atomic states. These don't violate light speed, they manipulate how light interacts with matter. We're learning to dance with the limit, not break it. Quantum computing promises revolutionary advances while respecting boundaries. Quantum entanglement enables parallel processing impossible for classical computers. Shor's algorithm factors large numbers exponentially faster. Quantum encryption provides theoretically unbreakable security. But quantum computers can't solve problems faster than light. They explore solution spaces differently, not faster. The speed limit constrains even quantum information. Energy considerations make light speed fundamental. Accelerating mass requires force times distance, work. Near light speed, tiny speed increases demand, enormous energy. The Large Hadron Collider consumes 120 megawatts accelerating protons. Reaching higher energies requires larger accelerators or revolutionary techniques. Future colliders might span countries, but they'll never push particles past light speed, only asymptotically closer. Cosmic rays demonstrate nature's own accelerators. Ultra-high energy cosmic rays carry energies equivalent to fastballs despite being single protons. Their origins puzzle astronomers. What cosmic engine accelerates particles to 99.999999% light speed? Active galactic nuclei, gamma-ray bursts, or unknown phenomena? These natural experiments probe physics at energies no human accelerator can achieve. The Oh My God particle, detected in 1991, carried 300 quintillion electron volts, 40 million times more than LHC protons. It traveled so close to light speed that crossing the observable universe would feel like 20 seconds from its perspective. Time nearly stopped for this particle. Yet it still couldn't exceed the ultimate barrier. Even the universe's most extreme accelerations respect the limit. Relativity creates fascinating paradoxes that aren't really paradoxes. The ladder paradox, a ladder moving near light speed, fits inside a shorter garage due to length contraction. The twin paradox, one twin travels near light speed and returns younger than the stay-at-home sibling. The Ehrenfest paradox, a spinning disk's circumference contracts while radius doesn't. These seem contradictory, but resolve perfectly within relativity's framework. The universe is consistent, just counterintuitive. Cherenkov radiation provides a beautiful exception that proves the rule. When charged particles exceed light speed in a medium like water, they emit blue light, Cherenkov radiation. Nuclear reactors glow blue for this reason, but this isn't breaking the cosmic speed limit. Light slows to 75% in water. Particles can exceed this reduced speed while staying below vacuum light speed. It's like passing a car in a school zone. You're faster than them, but still under the universal limit. Tachyon searches continue despite theoretical problems. If faster-than-light particles exist, they'd have imaginary mass, travel backward in time, and require infinite energy to slow down to light speed. Every experiment hunting tachyons has failed. Cosmic ray showers, particle collisions, astronomical observations, no evidence anywhere. The universe seems committed to keeping everything subluminal. Science fiction writers have invented countless ways around light speed, each revealing deep human desires to transcend limits. Hyperspace, subspace, jump gates, stargates, imagination refuses imprisonment. Yet the best science fiction often embraces the limit, exploring its consequences. Ursula K. Le Guin's Ansible allows instant communication but not travel. Kim Stanley Robinson's generation ships take centuries between stars. These stories grapple honestly with isolation and time that light speed imposes. Real physics offers subtler possibilities. Closed time-like curves, permitted by general relativity's equations, could enable time travel without exceeding light speed. Rotating black holes might contain such curves. Tipler cylinders, massive rotating cylinders, could theoretically create them, but these require impossible conditions: infinite cylinders, naked singularities, or exotic matter. Math allows them, nature probably doesn't. The Unruh effect predicts accelerating observers see vacuum as warm radiation. Extreme acceleration could theoretically reveal new physics. Some speculate sufficiently violent acceleration might expose shortcuts through higher dimensions, but accelerations strong enough to test these ideas would destroy any known material instantly. We're limited by engineering, not just fundamental physics. Frame dragging around rotating massive objects slightly pulls spacetime along. Earth's rotation drags space, confirmed by Gravity Probe B in 2011 after decades of work. Near rotating black holes, frame dragging becomes extreme. Space itself orbits the hole. Could advanced civilizations exploit this for propulsion? Perhaps, but they'd still move through the dragged space at subluminal speeds. Variable speed of light cosmologies propose light speed changed over cosmic history. João Magalhães and Andreas Albrecht suggested faster light in the early universe could solve cosmological puzzles without inflation. John Moffat's theory has light speed decreasing over time. These remain controversial. Most observations support constant light speed across billions of years. Quantum gravity, merging general relativity with quantum mechanics, might reveal new possibilities. Loop quantum gravity suggests spacetime is granular at Planck scale, 10 to the negative 35 meters. String theory proposes vibrating strings in higher dimensions. These theories remain incomplete, but might reshape our understanding of speed limits at microscopic scales. The holographic principle radically reconceptualizes space. If reality is encoded on a distant boundary, our three-dimensional experience might be emergent, not fundamental. Distance and speed could be approximate concepts, valid only at macroscopic scales. This wouldn't enable faster-than-light travel, but might reveal that space and motion are illusions masking deeper reality. Condensed matter physics creates analogies to cosmic phenomena. Sound waves in Bose-Einstein condensates mimic properties of light in curved spacetime. Researchers create acoustic black holes where sound cannot escape. These tabletop experiments test ideas about horizons and information without requiring actual black holes. They respect their own speed of sound limits, analogous to light speed. Quantum biology discovers quantum effects in living systems. Photosynthesis uses quantum coherence for efficient energy transfer. Birds might navigate using quantum entanglement in special proteins. If life harnesses quantum mechanics, could future technology exploit similar tricks? Not for faster-than-light travel, but perhaps for communication and computation approaching theoretical limits. The simulation hypothesis suggests our universe might be computational. If true, light speed could represent the simulation's clock rate or maximum information transfer between nodes. We'd be software experiencing hardware constraints. This doesn't help us exceed limits. We're inside the system, but it reframes light speed as potentially arbitrary, chosen by simulators for unknown reasons. Astronomy keeps finding phenomena that seem to violate light speed, but don't. Quasar jets appear to move faster than light due to projection effects. When jets point nearly toward us, their apparent motion across the sky exceeds light speed. But this is illusion. The jets actually move at 99% light speed. Careful geometry reveals no violation. Quantum experiments push boundaries of understanding. Delayed choice quantum erasers seem to change the past retroactively. But information never travels backward. The past isn't changed, rather our knowledge of quantum states updates. These experiments highlight how counterintuitive quantum mechanics is, while confirming no superluminal signaling occurs. Metamaterials manipulate light in extraordinary ways. Negative index materials bend light backward. Transformation optics designs invisibility cloaks. Slow light stores optical information. Fast light makes pulses exit materials before entering. But group velocity exceeding light speed doesn't violate relativity. Information still travels at or below light speed. We're mastering light's behavior within fundamental constraints. Casimir effect demonstrates vacuum isn't empty. Parallel plates in vacuum experience attractive force from restricted quantum fluctuations between them. Some speculate exotic matter with negative energy density needed for wormholes and warp drives might be extracted from vacuum. But Casimir energy is tiny and probably unusable for propulsion. Vacuum engineering remains highly speculative. Time crystals, confirmed in 2017, show matter in perpetual motion without energy input. They oscillate in time like regular crystals repeat in space. This doesn't violate thermodynamics. They're in their lowest energy state. Time crystals can't generate energy or enable perpetual motion machines, but they reveal new phases of matter that might have unexpected applications. Magnetic monopoles, if they exist, would complete electromagnetic symmetry. Electric charges come alone. Magnetic poles always pair north-south. Monopoles appear in many theories, but haven't been observed despite decades of searching. Their discovery would revolutionize physics, but wouldn't enable faster-than-light travel. Even exotic particles respect causality. Dark matter and dark energy comprise 95% of the universe, yet remain mysterious. Dark matter's gravity holds galaxies together. Dark energy accelerates cosmic expansion. Neither interacts electromagnetically, so light passes through unchanged. Understanding them might transform cosmology, but probably won't provide shortcuts through space. The universe guards its secrets carefully. The Parker Solar Probe demonstrates humanity's drive to push boundaries within natural limits. Launched in 2018, it's gradually spiraling closer to the Sun, eventually passing within 4 million kilometers of the solar surface. At closest approach, it reaches 430,000 kilometers per hour, the fastest human-made object relative to the Sun. Yet this incredible achievement represents just 0.064% of light speed. Even our boldest missions remain humbled by the cosmic speed limit. Breakthrough. Starshot represents our most ambitious attempt to approach meaningful fractions of light speed. Using powerful laser arrays to push ultralight sails, tiny spacecraft could theoretically reach 20% light speed. The challenges are staggering. Lasers powerful enough to propel but not destroy the sails, navigation systems that work for decades without maintenance, communication across light years with transmitters smaller than smartphones. Yet nothing in physics forbids it. We're engineering within reality's rules, not breaking them. The interstellar medium poses unexpected challenges for high-speed travel. Space isn't empty. Hydrogen atoms, cosmic dust, and radiation permeate the void. At 20% light speed, hitting a dust grain releases energy like a bomb. Spacecraft need shielding or routes through cleaner regions. The faster you go, the more dangerous space becomes. Light speed isn't just hard to reach, approaching it makes space itself hostile. Pulsar timing arrays search for gravitational waves from supermassive black hole mergers. By monitoring millisecond pulsars across the sky, astronomers detect space-time ripples stretching and squeezing Earth. These waves travel exactly at light speed, taking millions of years to reach us from distant galaxies. The 2023 announcement of a gravitational wave background confirms Einstein's predictions on cosmic scales. The cosmic web structure reflects light speed's influence across billions of years. Dark matter halos attracted regular matter, forming galaxies where filaments intersect. Information about density fluctuations traveled at light speed, determining which regions could communicate and cluster. The universe's large-scale structure literally embodies the speed of light frozen into patterns spanning hundreds of millions of light years. Redshift surveys map the universe in 3 dimensions plus time. Light from distant galaxies stretches as space expands during its journey. By measuring redshift, we determine distance and look-back time. The Sloan Digital Sky Survey has mapped millions of galaxies, revealing cosmic architecture. Each data point represents light that traveled millions or billions of years. We're archaeologists using light speed as our chronometer. Type II supernovae occur when massive stars exhaust nuclear fuel and collapse. The core rebounds, blasting outer layers into space at thousands of kilometers per second. Neutrinos escape immediately, but light takes hours to work through the explosion. Supernova 1987A in the Large Magellanic Cloud confirmed this. Neutrino detectors triggered hours before telescopes saw brightening. Even in stellar death, different messengers respect light speed differently. Fast radio bursts remain partially mysterious despite recent progress. Millisecond radio flashes from distant galaxies release as much energy as the Sun emits in days. Some repeat, others don't. Magnetars, neutron stars with extreme magnetic fields, cause many. But details puzzle astronomers. These cosmic flashbulbs probe intergalactic space, their dispersion through plasma revealing matter distribution. Light speed turns them into cosmic probe beams. The Moon's laser-ranging experiments measure Earth-Moon distance to millimeter precision. Retroreflectors placed by Apollo astronauts and Soviet rovers bounce laser pulses back to Earth. Round trip time reveals distance. Decades of measurements track the Moon's slow spiral away from Earth at 1.5 inches yearly. This simple experiment confirms general relativity, tests alternative gravity theories, and depends entirely on light's constant speed. Mars exploration showcases light speed delays in practical engineering. Curiosity and Perseverance rovers navigate autonomously because commands take 4 to 24 minutes each way. Landing sequences execute pre-programmed instructions. Engineers watch helplessly as events that already occurred play out. The 7 minutes of terror during entry, descent, and landing happen before Earth even knows they've started. Light speed forces us to build smart robots, not remote-controlled toys. The Voyager missions, launched in 1977, still communicate despite being over 15 billion kilometers away. Signals take over 21 hours each way. Commands sent today won't be received until tomorrow. Responses arrive the day after. Engineers must predict Voyager's needs days in advance. These aging spacecraft, powered by plutonium batteries slowly dying, whisper across the void at light speed, humanity's most distant voices. New Horizons' Pluto encounter in 2015 required extraordinary planning. At 3 billion kilometers, signals took 4.5 hours each way. The spacecraft executed its flyby sequence entirely autonomously, gathering data while Earth waited anxiously. When confirmation finally arrived, Pluto had already shrunk to a dot behind the spacecraft. We explored a world in past tense, celebrating events hours after they occurred. The square-kilometre array under construction in Australia and South Africa will be radio astronomy's most powerful instrument. Thousands of dishes spread across continents will act as one telescope, using light-speed signals to synchronize observations. Processing exabytes of data daily, it will map hydrogen throughout cosmic history, detect gravitational waves through pulsar timing, and search for extraterrestrial intelligence. Light speed enables and constrains this continental-scale instrument. Optical SETI searches for laser signals from alien civilizations. Unlike radio, lasers can outshine stars at specific wavelengths, making them ideal interstellar beacons. Automated telescopes scan millions of stars for nanosecond flashes. Nothing yet, but the search has barely begun. If aliens signal with lasers, those photons travel at standard light speed. No faster message exists. Contact means patient waiting for light to crawl between stars. The Fermi paradox deepens when considering light speed. If the galaxy is billions of years old and contains hundreds of billions of stars, where is everybody? Even at 1% light speed, colonization could spread across the galaxy in 10 million years. An eye blink, cosmically. Either we're among the first intelligent species, life is extraordinarily rare, or something prevents galactic colonization. Light speed shapes all scenarios. Cultural evolution accelerates while physical travel crawls. By the time a generation ship reaches another star, centuries or millennia have passed on Earth. Colonists would arrive speaking languages their ancestors wouldn't recognize, practicing religions that didn't exist at departure, using technologies unimaginable when they left. Light speed doesn't just separate us in space, it fragments humanity across time. Each interstellar journey creates a new branch of human civilization, forever isolated by physics. The overview effect transforms astronauts who see Earth from space. They describe profound cognitive shifts, seeing humanity as one species on a fragile world without borders. But imagine the galaxy view effect, seeing the Milky Way from outside, our 100 billion stars a mere smudge among trillions of galaxies. Would such perspective humble us further or inspire greater ambitions? Light speed ensures few humans will ever experience this ultimate overview. Quantum archaeology proposes recovering information about the past through quantum correlations. Every particle interacting leaves subtle traces. Advanced civilizations might reconstruct historical events by analyzing present quantum states, but information still can't travel faster than light backward. We might someday read the universe's history written in quantum signatures, but we can't change it or communicate with it. The past remains fixed, preserved by causality. The Great Filter hypothesis suggests some step from non-life to galaxy-spanning civilization is extremely improbable. Is it abiogenesis, multicellularity, intelligence, technology? Or does light speed itself filter civilizations, making interstellar expansion so difficult that none succeed? Perhaps millions of intelligent species exist, all trapped in their stellar neighborhoods by physics. The universe might teem with isolated islands of thought. Stellar engineering represents thinking beyond planets. Dyson spheres could capture a star's entire output. Shkadov thrusters could move stars themselves, slowly migrating across galaxies over millions of years. These megastructures respect light speed. Even moving stars can't exceed it. But they represent patience on geological timescales, civilizations thinking in eons rather than years. Light speed might not trap us, but teach us cosmic patience. The Kardashev scale classifies civilizations by energy use. Type 1 harnesses a planet's energy. Type 2 captures a star's output. Type 3 controls galactic energy. Each leap represents roughly 10 billion times more power. But even Type 3 civilizations can't exceed light speed. They might engineer galaxies, but information still crawls between stars. Power doesn't overcome fundamental limits, it just operates within them more grandly. Biosignatures in exoplanet atmospheres might reveal life light years away. Oxygen plus methane suggests biology. Both gases react quickly without replenishment. James Webb Space Telescope examines nearby exoplanets' atmospheres, searching for life's fingerprints. But these observations show ancient history. A biosignature from 40 light-years away reflects life from 1984. By the time we detect alien biology, it might have evolved beyond recognition or vanished entirely. The Drake equation estimates communicating civilizations in our galaxy. Factors include star formation rates, planetary frequencies, life emergence probability, intelligence evolution, and civilization lifetime. Light speed affects the final factor crucially. If civilizations typically last only thousands of years, the galaxy might host millions of extinct civilizations but few contemporaneous ones. We're searching for needles in a haystack where most needles have already rusted away. Panspermia suggests life spreads between worlds via meteorites or comets. Microbes surviving in rocks blasted from one planet could seed another. Mars meteorites found on Earth prove material exchanges occur, but even panspermia respects light speed. Life might hop between stars over millions of years, but it's a slow, random walk, not directed expansion. The universe might be a garden where seeds drift on cosmic winds. The transcension hypothesis proposes advanced civilizations turn inward rather than outward. Instead of expanding through space, they might compress into ever smaller, more efficient substrates. Black holes could be ultimate computers, processing information at physical limits. This would explain the Fermi paradox. Advanced intelligence becomes invisible, not absent. They transcend rather than expand, leaving the universe apparently empty. Time dilation offers subjective shortcuts. At 99.99% light speed, time slows by a factor of 70. A journey to Andromeda would take 2.5 million years for outside observers, but only 35,000 years shipboard time. Push closer to light speed, and subjective time shrinks further. Travelers could cross the observable universe in decades of personal time while billions of years pass outside. But they'd return to an unrecognizable universe where their origin civilization is ancient history. Relativistic kill missiles represent a dark possibility. A spacecraft at 99% light speed carries kinetic energy equivalent to its mass in antimatter. A 1-ton probe could devastate a planet. This makes interstellar war terrifying. Attacks could come from any direction with almost no warning. Some suggest this explains the Great Silence. Civilizations hide because revealing location invites relativistic bombardment. Light speed makes the universe a dark forest where exposure means death. The anthropic principle gains strength from light speed's precise value. Slightly faster, and particles couldn't form stable atoms. Slightly slower, and stellar fusion wouldn't work. We exist in a narrow window where chemistry, biology, and intelligence are possible. This isn't mystical. Observers necessarily find themselves in observable universes, but it suggests our cosmic situation is special, balanced on a knife's edge of physical constants. Vacuum decay represents an ultimate catastrophe. If the Higgs field isn't at true minimum energy, it could quantum tunnel to a lower state. This would create a bubble of different physics expanding at light speed, destroying everything it touches. We couldn't see it coming. It arrives at light speed. The universe could end tomorrow from a vacuum bubble born billions of light years away. Light speed limits threats, but also warnings. The cosmic censorship hypothesis suggests singularities hide behind event horizons. Naked singularities where physics breaks down visibly might be forbidden by nature. Black holes cloak their mysteries where light cannot escape. This protects causality. Infinite densities can't send signals to corrupt the universe's logic. Light speed creates cosmic modesty veils, hiding physics' embarrassing breakdowns. Consciousness itself might emerge from light speed's constraints. Neural signals propagate at mere hundreds of kilometers per hour. Glacial compared to light, but still electromagnetically limited. The binding problem asks how distributed brain processing creates unified experience. Perhaps the finite speed of neural communication creates the temporal flow we experience as consciousness. Without signal delays, would awareness exist as we know it? Light speed might not just limit our bodies but create our minds. The simulation argument gains credence from quantum mechanics and relativity. Both theories suggest reality isn't as solid as it appears. Quantum fields fluctuate probabilistically. Spacetime bends and warps. If reality is information-based rather than substance-based, light speed could be the universe's clock cycle, the maximum rate at which reality updates itself. We might live in a cosmic computation where physics emerges from information processing. Closed time-like curves haunt general relativity's equations. Near rotating black holes or in contrived spacetimes, world lines could loop back to their own past. But every examined case requires exotic matter or infinite structures. Nature seems to abhor time travel paradoxes. Stephen Hawking's chronology protection conjecture suggests physics conspires to prevent time machines. Light speed might be just one guardian among many protecting causality. The multiverse concept offers infinite variations on physical laws. String theory suggests 10 to the 500 possible vacuum states, each with different constants. Most would be sterile, no atoms, no stars, no observers. We necessarily find ourselves in a rare, hospitable universe. Other universes might have different light speeds or no speed limit at all, but we can't visit them to check. Even infinite realities can't overcome the barriers between them. Quantum computers promise exponential speed-ups for specific problems while respecting light speed. They explore superpositions of solutions simultaneously rather than sequentially. but extracting answers requires measurement collapsing superpositions. Information still can't exceed light speed. Quantum advantage comes from parallelism, not velocity. Even quantum information obeys Einstein's ultimate limit. The black hole information paradox challenges our understanding. Information falling into black holes seems destroyed when the hole evaporates via Hawking radiation. But quantum mechanics demands information preservation. Recent insights suggest information escapes subtly encoded in radiation, but the details remain murky. Resolving this paradox might revolutionize physics, but likely won't overthrow light speed limits. Cosmic inflation solved multiple cosmological puzzles by proposing rapid early expansion. Quantum fluctuations stretched to cosmic scales became seeds for galaxies, but inflation itself poses puzzles. What started it? What stopped it? Could it happen again? Some models suggest eternal inflation where universe bubbles constantly form. Our observable universe might be one bubble among infinite others, all separated by inflating space forever. Dark energy accelerates cosmic expansion, discovered through distant supernovae appearing dimmer than expected. Space itself gains energy as it expands, driving faster expansion. Eventually, all galaxies beyond our local group will disappear beyond the cosmic horizon. The observable universe shrinks even as total space grows. Future astronomers might see only our galaxy, unaware of the cosmos beyond. Light speed can't keep pace with accelerating space. Modified gravity theories attempt explaining cosmic acceleration without dark energy. Modified Newtonian dynamics, tweaks gravity at low accelerations. TVES and other relativistic versions respect light speed while altering gravity, but gravitational wave observations constrain modifications severely. Gravity waves travel at light speed precisely, killing many alternative theories. Einstein's vision survives increasingly stringent tests. The firewall paradox suggests black hole horizons might incinerate in falling matter rather than letting it pass smoothly. Quantum entanglement between Hawking radiation and interior states creates contradictions. Resolving this might require new physics at horizon scales, but even firewalls wouldn't violate light speed. They'd just make black holes even more hostile to visitors. Every solution respects causality's ultimate guardian. Warp drive research continues despite daunting challenges. Harold White at NASA calculated reducing energy requirements by oscillating the warp bubble. Others propose using Casimir energy or hypothetical dark energy, but all designs need exotic matter that probably doesn't exist. Even if possible, creating the initial warp bubble might require faster-than-light coordination. The catch-22 persists. You need FTL to achieve FTL. The M-drive controversy illustrates how desperately we want to transcend limits. This reactionless thruster supposedly generated thrust without propellant, violating conservation of momentum. Initial tests showed tiny forces sparking excitement, but refined experiments revealed measurement errors from thermal effects and electromagnetic interactions. No free lunch exists. Every proposed shortcut eventually hits fundamental barriers. Quantum entanglement enables new technologies within light speed limits. Quantum key distribution provides theoretically unbreakable encryption. Quantum teleportation transfers quantum states between particles. But classical communication at light speed must accompany these processes. You can't send messages through entanglement alone. Nature permits quantum weirdness but protects causality zealously. The cosmic web maps dark matter's gravitational influence across billions of light years. Galaxies form along filaments where dark matter concentrates. Voids between filaments span hundreds of millions of light years with few galaxies. This structure emerged from quantum fluctuations inflated to cosmic scales, then shaped by gravity over billions of years. Light speed determined which regions could gravitationally communicate during structure formation. Primordial black holes might have formed from extreme density fluctuations in the early universe. Unlike stellar black holes, they could have any mass. Some might be planet-sized or smaller. If they exist, they'd be dark matter candidates. But even primordial black holes respect light speed. Their event horizons trap everything, including light. They're not shortcuts, but dead ends in space-time. The cosmic microwave background reveals the universe's baby picture from 380,000 years after the Big Bang. Temperature fluctuations of 1 part in 100,000 seeded all structure we see today. These tiny ripples, stretched across the sky, encode information about inflation, dark matter, and cosmic geometry. But this information traveled 13.8 billion years to reach us. We see the universe's infancy because light speed preserves ancient history. The pursuit of knowledge itself is a process bound by light speed. Every scientific paper, every new measurement from Hubble or Webb, every theory shared at a conference, all must travel through space and time. Discovery is inherently delayed. When physicists at CERN confirm a new particle, that knowledge takes time to propagate across the globe, let alone across the galaxy. This shared, slow accumulation of fact is what defines human science. Consider the time required for any civilization to become truly spacefaring. A journey across the Milky Way takes thousands of years, even near light speed. A civilization must maintain social cohesion, economic stability, and scientific purpose across epochs. Light speed imposes a temporal bottleneck on galactic expansion. Any civilization that spreads widely must learn to master vast timescales, mastering patience across generations. This patience is something we, living on a fast-moving planet with instantaneous digital communication, often lack. We want answers now. We crave instant travel. But the universe operates on longer rhythms, dictated by the speed of light. Learning to appreciate these longer scales, with the billion-year lifespan of a star, the million-year drift of a galaxy, is essential for truly joining the cosmic story. The next great leap in understanding might not be about breaking light speed, but understanding what it truly connects. Is the speed of light a constant in all realities, or is it merely a local feature of our specific bubble of space-time? Competing theories of quantum gravity offer different answers. Experiments probing the constancy of light speed over cosmic history, looking at high-energy gamma-ray bursts, for example, offer slight hints but no definitive proof of variation. The precision of measuring light speed itself is a testament to human achievement. From Romer's timing of Jupiter's moons in the 17th century to modern laser interferometry, measurement techniques have become incredibly fine. This precision allows us to test relativity against other gravitational theories. If light speed varied even slightly depending on direction or energy, it would necessitate a complete rewriting of our fundamental physics texts. The existence of the cosmological constant, tied to dark energy, suggests that even the vacuum of space possesses energy that drives expansion faster than light. This is space expanding, not objects moving, but it emphasizes that the universe is dynamic, not static. Light speed governs movement within the space-time grid, but the grid itself is stretching independently. This interplay between local constraints, light speed, and global dynamics, expansion, is where the grand story of cosmology unfolds. We look out and see galaxies receding at ever-increasing speeds because the space between us stretches faster than light, effectively cutting them off from future communication. The speed limit enforces a horizon on the knowable universe. The search for life elsewhere is inherently a search into the past due to light speed. Finding an Earth-like planet around Tau Ceti today tells us about its state roughly 12 years ago. If that planet hosts life, we're seeing ancient echoes. If that life develops intelligence and decides to send a signal, we won't receive it until 12 years after they send it. Every contact attempt involves massive temporal lag. The mystery of dark matter, which outweighs visible matter by a factor of 5, looms large. We detect its gravitational influence everywhere, from galaxy rotation curves to gravitational lensing, but we can't see it because it doesn't interact electromagnetically. Light passes right through it. If dark matter particles move at various speeds, some could approach light speed, but they remain elusive shadows shaping the cosmic structure without ever interacting with our light-based science. Even seemingly simple light phenomena reveal profound cosmic connections. The faint glow of air glow on Earth at night is caused by atoms absorbing and re-emitting sunlight. This light, generated by our own star, travels at light speed to warm our atmosphere. We are bathed in the ongoing process of the universe, a continuous exchange of energy governed by this ultimate rate limit. We must encourage critical thinking about sensational claims. Every few years, a fringe scientist announces faster-than-light communication or propulsion. These usually rely on misunderstanding time dilation, confusing phase velocity with signal velocity, or misinterpreting quantum phenomena. Holding firm to verified principles like relativity prevents us from wasting resources chasing pseudoscience, keeping our focus on the engineering challenges that can be solved within known physics. The very stars we observe are products of stellar evolution governed by light speed. Nuclear fusion in the core generates energy, and that energy takes thousands of years to bounce its way out to the surface, finally streaming away as photons traveling at light speed to reach us. The longevity and stability of stars, prerequisites for life, depend on this slow, constrained energy transfer process. Gravitational lensing transforms massive objects into natural telescopes. Galaxy clusters bend light from more distant sources, magnifying and distorting their images. The Hubble Space Telescope captured spectacular examples like the cosmic horseshoe and Einstein rings. Some lensed galaxies appear multiple times, each image showing different moments as light traveled various paths. We see cosmic instant replays, time delays measured in years. Light speed turns gravity into a time machine, showing us the same events from multiple angles across time. The Pioneer anomaly puzzled scientists for decades. Pioneer 10 and 11 spacecraft experienced tiny, unexpected decelerations while leaving the solar system. Some proposed new physics, modifications to gravity, or unknown forces. After exhaustive analysis, thermal radiation from the spacecraft's plutonium power sources explained the effect. Even tiny forces matter in the vacuum of space. The anomaly's resolution reinforced known physics rather than revealing shortcuts past light speed. Breakthrough. LISTEN scans millions of stars for technological signatures. Using the world's most powerful radio telescopes, it searches for narrow-band signals, laser pulses, or other artificial patterns. Machine learning algorithms sift through petabytes of data. Nothing yet, but the search has barely begun. If signals exist, they crawl toward us at light speed. A detection would be monumental but also historical, news from a civilization that might no longer exist. The weight calculation suggests we shouldn't expect contact soon. If civilizations are rare and randomly distributed, the nearest might be thousands of light years away. Their signals haven't had time to reach us since we developed radio technology. We might need centuries of listening before detection becomes probable. Patience isn't just a virtue in SETI, it's a mathematical necessity imposed by light speed and cosmic distances. Stellar aberration proves Earth's motion through space. As Earth orbits the Sun, stars appear to shift position slightly, like rain seeming to slant when you run. James Bradley discovered this in 1727, providing early evidence for light's finite speed. modern measurements detect aberration to micro-arc-second precision. This simple effect, visible in backyard telescopes, demonstrates our motion through a universe where light speed stays constant. The twin paradox isn't really paradoxical once properly understood. One twin travels near light speed while another stays on Earth. The traveler ages slower, returning younger than their sibling. But there's no symmetry. The traveler accelerates, changing reference frames. Acceleration breaks the symmetry, determining who ages less. GPS satellites experience this daily, their clocks running faster, in weaker gravity and slower from orbital motion. Engineers must account for both effects precisely. Cosmic rays shower Earth constantly, mostly protons accelerated by supernovae, pulsars, or active galactic nuclei. The highest energy cosmic rays carry as much energy as a baseball pitch concentrated in a single proton. They travel so close to light speed that crossing the galaxy takes mere seconds from their perspective. But from our view, they've been traveling for millions of years. These particles are messages from cosmic accelerators, limited by the same speed governing everything else. The GZK cutoff limits cosmic ray energies from distant sources. Protons above 50 exa-electron volts interact with cosmic microwave background photons, losing energy. This creates a horizon beyond which ultra-high energy cosmic rays can't reach us. The universe becomes opaque to its own highest energy particles. Even cosmic accelerators face limits imposed by light speed and quantum mechanics working together. Photon spheres exist around black holes where light orbits in unstable circles. At exactly 1.5 times the event horizon radius, photons can orbit indefinitely if undisturbed, but the slightest perturbation sends them spiraling inward or escaping outward. These regions demonstrate light's subjugation to gravity. Even massless photons follow curved paths in warped spacetime, trapped by their own speed limit. The Shapiro delay makes light take longer paths through curved spacetime. Radio signals passing near the Sun arrive slightly delayed compared to straight-line expectations. Viking spacecraft measured this precisely in the 1970s, confirming general relativity. Space missions now routinely account for Shapiro delay in navigation. Light doesn't always take the shortest path. It takes the fastest path through curved spacetime, which isn't always straight. Tired light cosmology attempted explaining cosmic redshift without expansion. Perhaps photons lose energy traveling vast distances, shifting toward red, but this fails multiple tests. Distant supernovae would appear blurred if photons decayed randomly. Time dilation in supernova light curves matches expansion predictions perfectly. The cosmic microwave background's black body spectrum rules out tired light. The universe really is expanding, not just appearing to. Frame dragging near rotating masses slightly pulls space-time along. Earth's rotation drags space, making satellites precess slowly. Near rapidly spinning black holes, frame dragging becomes extreme. The ergosphere is a region where space itself rotates faster than light relative to distant observers. Objects can't remain stationary there, they must orbit with the dragged space. Yet nothing exceeds light speed locally. Even in the universe's most extreme environments, the speed limit holds. Quantum foam might texture space-time at the smallest scales. Virtual particles constantly appear and annihilate in vacuum fluctuations. At Planck length, 10 to the negative 35 meters, space-time might seethe with quantum uncertainty. Some theories suggest this foam could affect light propagation over cosmic distances. Observations of distant gamma-ray bursts constrain such effects severely. Even quantum gravity respects light speed at observable scales. The information paradox extends beyond black holes. If information can't be destroyed, where does it go when matter enters a black hole? Recent theories suggest information spreads across the event horizon, encoded holographically. The three-dimensional interior information maps onto the two-dimensional surface. This holographic principle might apply everywhere, not just black holes. Reality could be fundamentally two-dimensional, with our three-dimensional experience emerging from information on a distant boundary. Cosmic strings, if they exist, would be one-dimensional defects from phase transitions in the early universe. Thinner than atoms, but potentially light-years long, they'd gravitationally lens light distinctively. Despite searches, none have been found. Even these exotic objects would respect light speed. They might wiggle and oscillate, but vibrations would propagate along them at or below light speed. The universe permits strange structures, but not causality violation. But have you ever wondered how far we can actually travel across space? Then check out this video at the left side of the screen. In this comprehensive deep dive into space exploration, discover why the farthest humans have ever traveled. Learn about revolutionary propulsion technologies, including ion drives that accelerate particles to 90,000 kilometers per hour, solar sails using light pressure for interstellar missions, fusion rockets that could reach 12% light speed, and the theoretical breakthrough Starshot project aiming for 20% light speed to reach nearby stars in just 20 years, and much more.